Great. So now that we've talked through some of these basics here about the Bootstrap sample and the Bootstrap statistic and why we're doing all this, let's actually talk through how we create this Bootstrap distribution and this Bootstrap interval to actually answer our question about estimating the mean or proportion of something in the population. So how do we actually make this interval to answer our research question? So we talked through some parts of this already, but we do sampling with replacement from our original sample. We write down whatever the measure of interest is that we care about, whether it's average income, average height, percentage of blue dots. Mark that down. And then we repeat this process of sampling with replacement up to the sample size of the original sample and measuring the sample statistic however many times we think is sufficient. And as we'll see in this course, you will do that 10,000 times with the software, which we'll get to in a second. And when we do this, as you will see, we will be able to obtain a measure of variability called the standard error. And in order to make our interval, which is just one number to another number, we take our original sample statistic and go up 2 standard errors and down 2 standard errors. And this thing is called the 95% confidence interval. So that's the high-level summary of it. To drive it home, let's do 2 examples, and we'll go through it step by step. Okay, in this first example, let's say that our population of interest is all M&Ms that are currently in existence. Let's say, the ones that haven't been eaten. Just all the M&Ms that are currently out there. And we want to know what proportion of all of those M&Ms are blue. So ideally, we would find every M&M in existence and count up how many blues there are and find out the proportion. And that would answer our question directly. But we don't reasonably have access to every M&M in existence right now. So we can take one sample. And again, what would be really nice is if we could take a bunch of samples, just over and over and over again. Take a bunch of samples of M&Ms and get an estimate for how much that proportion of blues jumps around due to taking repeated samples. But it may be very impractical, again, to take repeated samples of things. So we're going to answer this question to estimate the proportion of all M&Ms that are blue using an interval created from a Bootstrap distribution, from a Bootstrap sampling approach. So for our example, let's say that we have a sample that we took of 20 M&Ms, and 4 of them are blue. So right away, I will X out of this for now because I'm going to skip over. Right away, my sample proportion is 4 out of 20, or 1/5, or 0.2. So I could say, I estimate in the population that the proportion of blues is 0.2, or that the percentage of blues is 20%. But that's just one sample of 20. Maybe that was a really low blue sample, or maybe it was a really high blue sample. I want to estimate how much this proportion of blues might jump around, only with the information in this one sample. So here's how we do this, and here's what you're going to be doing to do this. Since I want to estimate the proportion of something, I'm going to be making a confidence interval for a proportion. In all my different options here in StatKey, here is our second column here has our different bootstrap confidence intervals, as they're called. And we'll use most of these in this course. But all I need right now is the confidence interval for a single proportion. Now, when you click on this, it's going to have some pre-made data and example already loaded. And if I check, in this case, these pre-made data examples here are of, different kinds of things that are already in here. But I don't want these pre-made examples. I want to use my example of 20 M&Ms, 4 of which are blue. So to do this, I can click on Edit Data, and notice it only requires 2 pieces of information. The sample size is 20, and the count is the count for the thing that I'm interested in. In this case, I'm interested in blue M&Ms. So in my original sample, what's the count for blue M&Ms? Well, we know it's 4. That's the information we've been given. This is the minimum information you need to answer a question about the proportion of something in a population. Now I hit OK, and this up here has my original sample, a count of 4, a sample size of 20, and the original sample proportion of 0.2. Now, to generate a Bootstrap sample, all I need to do is click Generate One Sample. What it gives me is 2 things. First, it shows me the results of that Bootstrap process. So in this case, in this Bootstrap simulation, this one simulated Bootstrap sample, I got 3 blue M&Ms. Because we're bootstrapping, we know our sample size is going to be the same as the original. So it's still 20. And 3 divided by 20 is 0.15. So behind the scenes, what you see is this process we talked about, where it took out an M&M, it marked down its color, and then it put it back. It sampled with replacement in the original 20. And then it did it again and again and again until it had 20. And then it said, how many blues are there? In this case, there are 3. And on this big area is where we will see the different Bootstrap statistics. In this case, for this one Bootstrap sample, the Bootstrap statistic is 0.15. That's the proportion of blues from this Bootstrap sample. So what does it do? It plots 0.15, a single dot on this main graphing area. And that's it. If I want to generate another Bootstrap sample, I can do it again. This now has updated to show me the results from the most recent Bootstrap sample. In this case, for this second one, I had 2 blues come up for a sample proportion of 0.10. And there it is, 0.10. Notice that after doing 2 Bootstrap samples and getting 2 different Bootstrap statistics, I've got a mean down here developing of 0.125, and I have my 2 Bootstrap statistics that I ran, 0.15 and 0.10. So if I keep hitting Generate One Sample, you'll see that I start getting different estimates for the proportion. And I'll do 10 of these. And the most recent one, the 10th one, I got 6 with first sample proportion of 0.3. Excuse me, a Bootstrap statistic, yes, sample proportion of 0.3. And there it is. And I can look at this, and out of these 10, I can start to see, yeah, there's some sampling variability. I can start to see where the population, the true population proportion of M&Ms, blue M&Ms, might be. Well, 10 isn't very much. So I'm going to generate 10,000 more by clicking this Generate 1,000 Samples button. And every time I hit that, it generates another 1,000 Bootstrap samples. And you can see the count going up here. Now I'm at 5,010, 6,010, 7,010, 8,010. I want to get up to 10,000. That is a good number for our purposes. Great. So now this whole thing is called a Bootstrap distribution. It is composed of 10,010 individual Bootstrap samples of size 20. The 1,010th Bootstrap sample had a count of 6, just for our information. And you can hover over each of these little things here. And this thing updates up here. So if I hover over the middle here, you see that now my Bootstrap sample is set at 4. I can go all the way down here, and now my Bootstrap sample is set at 0. So these are all the ones that had a Bootstrap sample count of 0. These are all the ones that had a Bootstrap sample count of 10. There's one with 11. So here we go. This demonstrates my variability in the proportion of blue M&Ms if I were to take repeated samples. So how do I make a confidence interval to estimate what the true proportion of blue M&Ms is in the population? Well, the mathematical way to do it, which I'll show you in this example here, is, if you remember from here, we take our original sample statistic and then go plus or minus 2 standard errors. So what's our original sample statistic? Well, that's our original sample proportion of 0.2. Great. So what's my standard error? So here's a little bit of a terminology issue. The standard error represents the variability of my proportion or mean over repeated samples. The standard error is a measure of sampling variability. In terms of what we get from StatKey, in terms of what we get from the Bootstrap distribution, the standard error is the standard deviation of this distribution. The standard deviation of all these dots, all these counts, this whole thing, the standard deviation, the typical deviation of my sampling proportions, my sample proportions from this middle here is 0.089, or about 0.09. So this 0.0 will round up to 9. This 0.09 is the standard deviation of all of these Bootstrap samples. And that represents the standard error on the sample proportion, the sample proportion of blue M&Ms for the population I care about. Sorry for the pause there. So I plug in the 0.9 and I go up 0.09 twice, I go down 0.09 twice, and I get a confidence interval of 0.02 to 0.38. What this means, and we say, I am 95% confident that the population proportion of blue M&Ms is between 0.02 and 0.38. We say it's 95%. Hopefully you caught this from the book, because in general, it's a mathematical, it's a distribution thing. In general, 95%, let me back up for a second. We say 95% confidence because, in general, 2 standard errors up and 2 standard errors down covers 95% of these sample Bootstrap statistics. And mathematically, it is 95%, assuming a normal distribution. That's some more of the stat theory type things behind it. But I will pick up from this point in the next video, and we'll do one more example, and then that will be it. Thank you.